There's a quiet question that follows you when you look up at the night sky. Does the universe know what time it is? Not your time, not the numbers on your phone screen or the ticking of the kitchen clock, but a deeper time, the kind written into the fabric of reality itself. Out there, far beyond the hum of your home, stars are keeping a rhythm older than Earth. Galaxies drift, light bends, and ancient starlight arrives like postcards from billions of years ago. Time out there isn't just measured. It's woven into every atom, every shadow, every movement. And yet, here we are, trying to keep up with wristwatches, leap years, and daylight savings. Tonight we'll let go of our calendars. We'll follow the slow, patient heartbeat of the cosmos. You may feel yourself relax as the minutes stretch and your own thoughts begin to drift with them. Because when we listen to the universe's clock, we find a story that's as much about us as it is about the stars. The strange idea that the universe might have a clock. We're used to thinking of clocks as human inventions, gears, hands, digits on a glowing screen. But imagine a clock so vast, no single civilization could build it. A clock that doesn't just measure time, but defines it. This is the strange possibility that the universe itself might be keeping time, not in seconds or minutes, but in the rhythm of its own expansion. Astronomers look at the speed of galaxies moving away from us and see something remarkable. It's like a cosmic metronome, ticking not in beats but in billions of years. The question is, if there's a cosmic clock, who or what is it for? Sometimes I think about how small we are in that timeline. A human life is a fraction of a blink compared to the universe's day. Yet we've found ways to measure even the most elusive cosmic changes. We've learned to read light like a diary, each wavelength telling us not just where it came from, but when. That's the thing about cosmic time. It hides in plain sight, disguised as beauty. The streak of a comet, the faint glow of a distant star. They're all hands on an unseen clock. The strangeness is, unlike our clocks, this one doesn't start and stop. It doesn't wind down, it doesn't tick faster when you're late for work. It flows, like a river without a beginning or an end we can truly see. Scientists call this cosmic time, and it's not something we can touch, only observe, piece by piece. And yet, every observation becomes part of its record. We are, in a way, both the watchers and the watched, but even that description feels too human. The universe's clock isn't interested in us. It ticks in the collapse of dying stars, in the slow fade of galaxies slipping beyond sight. It's almost unnerving to realize that the clock doesn't need an observer to keep running. It would tick whether we were here or not. That kind of time feels ancient, impartial, and strangely comforting. And perhaps the most humbling part, if the universe has a clock, then everything, every atom, every breath, is part of its schedule. We're not late, we're not early. We're exactly where the universe's time says we should be. How time feels different when you're awake at night. There's a peculiar stillness in the hours when the world sleeps. Your body knows it's late, but your mind feels like it's floating. Minutes feel longer or shorter, sometimes both at once. This is your brain without the usual cues of daylight, slipping into a slower rhythm. Scientists call this circadian drift, and it's one of the few times we notice how elastic time can feel. In those late hours, even the smallest sound feels amplified. A creak in the floor, the hum of a fridge. They're like markers in a quiet ocean. Out in space, similar shifts happen on a grander scale. When a spacecraft drifts into the shadow of a planet, its instruments detect changes. Tiny shifts in energy, in movement. It's a reminder that time isn't just about numbers, it's about sensation. This is why being awake at night can feel like being untethered from the day. your mind slips into a mode that's closer to how the universe keeps time, slowly, without urgency, guided by cycles rather than appointments. Maybe that's why stargazing feels so natural in the dark. Our thoughts stretch out, and we begin to measure moments the way the stars do. But it's not just poetic. Your body's chemistry changes at night. Melatonin rises, temperature drops, and brain activity patterns shift. These biological changes align with the Earth's rotation, which itself is synced to the cosmic rhythm of the sun. It's easy to forget, but when you lie awake at 2 a.m., you're still part of a much larger clockwork. And in that half-sleep haze, you might even sense the same truth astronomers do. Time feels different not because it changes, but because we do. The night invites us to slow down enough to notice it. The earliest moments after the Big Bang. To imagine the universe's clock, we have to wind it back, way back, to the first moments after the Big Bang. Not seconds, not even fractions of a second. We're talking trillionths of a second after time itself began. In that instant, everything we now know, matter, energy, space, was compressed into a state so dense and hot, the rules we live by didn't yet exist. Physicists call this the Planck epoch, a moment where time as we understand it barely had meaning. In that inconceivable heat, forces that are now separate, gravity, electromagnetism, were one. Imagine a world without boundaries between what pulls and what pushes. That was the start. And then something happened. The universe began expanding faster than the speed of light in an event we call inflation. From that moment, the clock began, not with ticking hands, but with the cooling of the cosmos, the formation of particles, the first hints of light. It's strange to think that the universe's first second was also its most dramatic, and yet traces of that beginning remain. The cosmic microwave background, a faint glow across the entire sky, is a photograph of that time, taken when the universe was just 380,000 years old. It's like finding a baby picture of reality itself. To this day, that ancient light keeps travelling toward us, reminding us that the universe's time isn't just an idea. It's written into the very light we see at night. How light first began marking cosmic history. Light is a storyteller. It carries the past across impossible distances, embedding moments in its waves. When we see a star, we're not seeing it now. We're seeing it as it was, sometimes millions or billions of years ago. Light doesn't just mark time, it is time in motion. When the first atoms formed in the early universe, light finally had the space to travel freely. Before that, it was trapped in a dense, hot fog of particles. The moment the fog cleared, photons began their journey, and that journey never stopped. Every beam of light we catch in our telescopes is a timestamp from when it began. What's haunting is that light also shows us what's gone. Some of the stars whose light reaches us tonight burned out long before human history began. We're seeing ghosts of moments that have already passed, frozen in the act of shining. This is why astronomers call the sky a time machine. With each deeper look, we travel further into the past, using light as our map. And somewhere in that glow, you can almost hear the steady ticking of the universe's hidden clock. It's humbling. Light doesn't hurry. It doesn't pause. It just moves, carrying moments across space until they find us. Ancient starlight as the universe's memory. Think of the universe as a mind that never forgets. Every event, every collision, every spark is recorded in light. That's why astronomers can reconstruct cosmic history, because the evidence is still arriving. Ancient starlight is like the memory of the cosmos, and we're learning how to read it. Some of the light we detect began its journey before Earth existed, before the sun existed. Imagine that. Messages older than the very home you stand on, arriving just now, softly, without fanfare. It makes you wonder, How many moments have we missed simply because we weren't here yet to see them? The James Webb Space Telescope, for instance, is peering so far into the past that it's seeing galaxies as they were just a few 100 million years after the Big Bang. Each image is a recovered memory pulled from the deep archive of the sky. And yet, this isn't nostalgia for the universe. It's simply the way it is. The past and present overlap, layered in light. When you look up, you're part of that story too. Your eyes are collecting the same memories that have travelled untouched for eons. The ticking rhythm of pulsars in deep space. Imagine a lighthouse, but instead of sweeping over a harbour, its beam sweeps across the galaxy. That's what a pulsar is. The ultra-dense, spinning remnant of a massive star, beaming out pulses of radiation with such precision they make our best clocks look clumsy. Some pulsars spin hundreds of times each second, never missing a beat. Their rhythm is so perfect that astronomers use them to measure tiny distortions in space-time itself. What's extraordinary is that these pulses can travel for thousands of years before reaching us and still arrive right on time. That's not just a cosmic clock. It's a clock that survives supernova explosions, cosmic dust, and the slow drift of galaxies. And the sound, if you convert those pulses into audio, feels like listening to the heartbeat of the universe itself. Even more intriguing, some pulsars orbit each other in binary pairs, their gravitational dance subtly altering their timing. These shifts allow scientists to detect things like gravitational waves passing through the galaxy. It's like feeling the faint ripple of a giant's footsteps in the dark. In a way, pulsars remind us that the universe's timekeeping is not abstract. It's carved into objects, into matter itself. When we listen to them, we're not just hearing a star's pulse. We're hearing the very structure of space-time being played like an instrument. Why the universe doesn't run on human time. We live in a world obsessed with schedules, alarms, deadlines, meetings. But step outside that, and you realize the universe has no interest in our calendar. Out there, events unfold on timescales so vast or so quick they barely fit into human language. A star can take millions of years to form, yet a supernova can outshine a galaxy in a single week. The cosmos doesn't measure on time or late, it just moves at its own pace. Our idea of a second is arbitrary, based on the vibration of cesium atoms in atomic clocks. Cosmic time, by contrast, is woven from the motion of planets, the expansion of space, the decay of particles. It doesn't care if it's Tuesday or July. It flows whether we count it or not. When you see a galaxy 10 billion light-years away, you're not just looking at distance. You're looking at a time when Earth itself didn't exist. That's the natural scale of the universe's clock. And it's humbling, because it means our entire recorded history is just a thin slice on its face. Maybe that's the quiet lesson in all of this. Our lives may be brief, but they still happen exactly within the cosmic schedule, just as they were always meant to. The hidden patterns in planetary orbits. If you look closely at the way planets move, you'll notice something hypnotic. They're not just circling the sun at random speeds. They're locked into intricate patterns, repeating over years, decades, and centuries. These patterns are so regular that ancient civilizations could predict eclipses and planetary alignments long before modern astronomy. Take Earth and Venus. Every 8 years, they form a near-perfect pentagram in the sky. Jupiter and Saturn, the gas giants, meet in what's called the Great Conjunction roughly every 20 years, like clock hands crossing on the cosmic face. These aren't coincidences. They're the result of gravitational relationships, the universe's quiet way of marking the passage of time. Some of these cycles are so long we've never seen them complete. Pluto's trip around the Sun takes 248 years, meaning no human has witnessed it twice in a lifetime. Even longer cycles exist in the slow wobble of planetary orbits, unfolding over tens of thousands of years. It's a reminder that we're part of a giant, elegant machine, one that's been moving long before we arrived and will keep moving long after. How Earth learned to measure its own days. Before humans invented clocks, the Earth already had one, its own rotation. Every sunrise and sunset is the ticking of that ancient mechanism. But Earth's rotation isn't perfectly steady. Over millions of years, it's been slowly slowing down, lengthening our days by fractions of a second. And we only know this because the planet has left us clues. Ancient coral fossils, for instance, record daily growth rings, showing that hundreds of millions of years ago, a year had more days, but each day was shorter. The moon, tugging gently at our oceans, is partly to blame, creating tidal friction that subtly drags Earth's spin. We've gotten so used to our 24-hour rhythm that it's strange to imagine a future where day means something different. Yet in the cosmic clock, that's inevitable. Our planet's timekeeping is not fixed, it's in constant slow-motion change. In this way, Earth isn't just a passenger in the universe's time, it's a participant, adjusting, drifting, yet always marking the passing moments in its own quiet way. The slow drifting of our planet's internal clock. Even inside the Earth, there's a clock ticking. The planet's core, a churning sphere of molten metal, is gradually cooling and shifting. These slow changes subtly affect our magnetic field, and even, in the tiniest way, our rotation. You'd never notice it in daily life, but over millennia, these changes add up. Scientists studying seismic waves have noticed that the inner core may actually be rotating at a slightly different speed than the rest of the planet. This internal motion could be part of Earth's deep timekeeping, a geological rhythm far slower than anything we live by. In a sense, our planet's heartbeat is not just the rising and falling of tides or the turning of seasons. It's this deep, invisible movement beneath our feet, keeping time in a language older than humanity. And though it's silent to us, it's as much a part of the cosmic clock as the spin of galaxies or the flash of a pulsar. The cosmic microwave background is a silent timestamp. Everywhere you look in the night sky, no matter the direction, there's a faint glow, invisible to your eyes but caught by sensitive instruments. This is the cosmic microwave background, or CMB. It's not just random static, it's the oldest light in the universe, left over from a time when the cosmos was just 380,000 years old. That light has been travelling ever since, stretched and softened by the expansion of space, until it now hums quietly in the microwave part of the spectrum. What makes it so remarkable is that it's uniform, almost perfectly the same in every direction, but with tiny temperature variations that map the seeds of galaxies. These patterns are frozen snapshots of the early universe, like the first page of a diary, and by studying them, scientists can determine the age of the cosmos, its composition, and even its fate. It's almost poetic. The universe left behind a timestamp for us, not in ink or stone, but in light. And it's been waiting, patiently, for billions of years for someone to learn how to read it. How gravity bends and stretches time itself. Imagine standing on a mountain and watching the clock on your wrist tick. Now imagine someone at sea level with the same clock, and theirs ticks more slowly. This isn't science fiction, it's gravity affecting time, a phenomenon predicted by Einstein's general relativity. The stronger the gravity, the slower time passes. In the presence of something as massive as a star or planet, space-time itself curves. Clocks, whether mechanical, digital, or biological, follow that curve. That means time is not a fixed universal beat, but a flexible fabric that responds to the mass around it. Astronauts on the International Space Station actually experience slightly less gravity than we do on Earth, and because of their speed, they also experience time a little differently. When they return, their clocks are ahead by tiny fractions of a second. It's a subtle reminder that even in our own lifetimes, time is not the same everywhere. Black holes and the illusion of frozen moments. Black holes take this bending of time to an extreme. The closer you get to the event horizon, the boundary beyond which nothing can escape, the slower time passes for you compared to the outside world. To a distant observer, it would seem as if you were frozen at the edge, never quite falling in. This effect is so powerful that if you watched a clock fall into a black hole, it would appear to tick slower and slower until it stopped entirely. But from the perspective of the clock itself, time would continue normally, right up until it crossed the horizon. What's fascinating is that the universe hides these extremes from casual view. You can't watch this process play out with your naked eye, yet it's happening in countless places right now, silently bending the rules we take for granted. Time dilation on the edge of light speed. Speed can also warp time. When you approach the speed of light, time for you slows down relative to someone who's not moving as fast. This means that astronauts traveling at near light speeds could, in theory, experience only a few years while decades or centuries pass back on Earth. This isn't just a theory, it's been measured. Particles called muons, created in the upper atmosphere, decay so quickly they shouldn't survive long enough to reach the ground. But because they're moving at near light speed, their internal clocks slow down, letting them travel farther than they should. It's a strange, almost unsettling truth. Time isn't a constant river. It's a shape-shifting current that changes depending on how you move through it. Why cosmic expansion changes our sense of now. When we talk about now, we usually mean the same moment everywhere. But in the universe, there is no universal now. As space expands, galaxies get farther apart, and light from them takes longer to reach us. This means our present view of them is actually their distant past. Because the expansion is accelerating, galaxies far enough away will eventually slip beyond a horizon where their light can no longer reach us. It's as if parts of the cosmic clock are slowly disappearing from our view. This shifting boundary blurs the idea of a shared moment. Out there, now can mean billions of years apart, depending on where you stand. And that's perhaps the most humbling thing about cosmic time. It refuses to be pinned down. It's fluid, relative, and always moving beyond our grasp. The moving frame of the solar system's journey. We tend to picture the sun as a fixed center, with planets calmly circling it. But in reality, the entire solar system is racing through the Milky Way at over 800,000 kilometers per hour. The sun is not stationary. It's orbiting the galaxy's center, pulling us along in a graceful, spiraling path. This motion changes our position in space constantly, meaning our cosmic address is never the same 2 moments in a row. This journey takes about 230 million years to complete a single lap. The last time we were in our current position, dinosaurs were just beginning to roam the Earth. Each turn of this galactic orbit is a tick in a clock so vast, we only experience a fraction of it in all of human history. And as we travel, the motion changes our frame of reference for measuring time. In physics, where you are and how you move affects how you experience now. The solar system's path is part of that, quietly shifting the backdrop of cosmic time without us even noticing. How atomic clocks keep Earth in sync with the cosmos. To measure time with absolute precision, scientists don't rely on the sun or stars. They use atomic clocks. These devices measure the vibrations of atoms, often cesium or rubidium, which oscillate at a constant rate no matter where they are. The second in our system is literally defined by a specific number of these oscillations. But even these perfect clocks must be adjusted for the effects of gravity, motion, and Earth's irregular rotation. GPS satellites, for example, carry atomic clocks that tick differently from those on the ground because of their speed and altitude. Engineers must correct for these differences so that our navigation systems stay accurate. It's remarkable to think that your phone's map app works because it accounts for relativity, the same physics that governs time on the scale of galaxies and black holes. In a way, every time you check your location, you're syncing with the universe's deeper rhythms. Leap seconds and the corrections to our human clocks. Despite our best technology, Earth doesn't spin like a perfectly balanced machine. Tidal forces, shifting weather patterns, and even earthquakes can subtly speed up or slow down the planet's rotation. These changes might be tiny, milliseconds, but over time they add up. To keep our clocks in sync with the actual rotation of the Earth, scientists occasionally insert a leap second into coordinated universal time. On those rare days, the last minute of the day has 61 seconds instead of 60. It's a small but humbling reminder. Even our most precise timekeeping has to bend to the will of the planet. We're not in control of time. We're negotiating with it, adjusting our schedules to match the slow breathing of Earth itself, the slow wobble of Earth's axis and its quiet impact. Earth's axis isn't fixed, it wobbles like a spinning top. This movement, called precession, takes about 26,000 years to complete a single cycle. Over time, it shifts the position of the stars in our sky and changes the timing of the seasons relative to our calendar. In ancient times, Polaris wasn't the North Star. Another star, Thuban, held that role. Thousands of years from now, a completely different star will take its place. These shifts happen so slowly that no single generation notices them, but they're another example of the long-term rhythms that shape life on Earth. This wobble also affects climate patterns over geological timescales, linking our planet's orientation to ice ages and warm periods. It's as if Earth has its own long, slow pendulum swinging silently in the background of human history. Why the moon is slowly stealing our time. The moon's gravity pulls on Earth's oceans, creating tides. But these tides also push back on the moon, transferring energy and gradually moving it farther away, about 3.8 centimeters per year. This process slightly slows Earth's rotation, making our days a tiny bit longer over millions of years. In the distant past, days were much shorter. Fossil corals show that hundreds of millions of years ago, there were over 400 days in a year, each one just over 21 hours long. As the moon drifts farther, the days will continue to lengthen, though we'll never notice it in our lifetime. It's a quiet exchange, time traded for distance, unfolding every moment without pause. And it's another reminder that cosmic time isn't just out there in the stars. It's here, shaping the length of the days we live in, how your body's circadian rhythm mirrors cosmic cycles. Inside you is a clock you didn't set. It's not digital, and it doesn't tick, but it governs when you wake, when you feel alert, and when you drift to sleep. This is your circadian rhythm, a biological cycle shaped over millions of years by the rising and setting of the sun. Light enters your eyes and signals your brain's master clock, the suprachiasmatic nucleus, to adjust your internal schedule. This rhythm is so deeply linked to the cosmos that when astronauts spend months in space, away from Earth's day-night cycle, they often need artificial light cues to stay in sync. It's a reminder that our bodies evolved with the turning of our planet and the steady movement of our star. Even when you travel to a different time zone, your body resists the change. It still follows its home rhythm for days, proving how much we're wired to the Earth's natural time. The effect of moonlight on ancient human sleep patterns. Before electric lights, the moon was the brightest object in the night sky. Its phases quietly influence the lives of our ancestors. On bright full moon nights, people often stayed awake longer, using the extra light to hunt, gather, or socialize. On darker nights, they slept earlier and longer. Modern studies show that even today, without noticing, our sleep duration can shorten by up to an hour in the days around a full moon. This isn't superstition, it's biology responding to light, just as it has for thousands of years. The moon was our first nightlight, setting the pace for activities after sunset. It's humbling to think that our rest, our dreams, and even our energy levels have been quietly shaped by an object 384,000 kilometers away. Why our ancestors slept in sync with the stars. For most of human history, the sky wasn't just decoration, it was the clock. Farmers knew when to plant by the position of certain constellations. Sailors navigated by the movement of stars across the horizon. Night after night, our ancestors lived under patterns that marked the passage of seasons and years. Without alarms or calendars, these star cycles naturally set people's waking and sleeping rhythms. The rising of Orion signaled winter. The appearance of the Pleiades marked the planting season. Sleep often came soon after nightfall, and waking happened with the first hints of dawn light. Even now, in remote places without artificial light, people's sleep schedules remain closer to these ancient patterns. It's a connection to the cosmos that modern life has nearly hidden, but not erased. The forgotten two-phase sleep of pre-industrial life. Historical records suggest our ancestors didn't always sleep in one long stretch. Instead, many practiced two-phase sleep. They would go to bed after sunset, wake for an hour or two in the middle of the night to pray, think, or talk, and then sleep again until dawn. This pattern matched the body's natural tendency to drift in and out of deep rest. Without artificial light to extend the day, the long nights of winter especially encouraged this rhythm. It's intriguing to think this pause in the night wasn't considered insomnia, but a normal, even useful part of life. It gave time for reflection, storytelling, and watching the stars when the world was at its quietest. How artificial light pulled us away from cosmic time. The invention of electric lighting changed everything. For the first time, we could choose to ignore the sun and moon, extending our days far into the night. While it brought progress and productivity, it also pulled us out of step with the cosmic rhythms we'd followed for millennia. Today, many of us live in a constant glow, from lamps, screens, and streetlights, blurring the line between day and night. Our bodies still try to follow the old patterns, but the cues are weaker, leading to shorter sleep, altered hormone cycles, and a sense of disconnection from the natural flow of time. This doesn't mean we can't reconnect. Even small acts, watching a sunset, dimming lights at night, or stepping outside to see the moon, help us feel the quiet pulse of cosmic time again. Jet lag as a symptom of fighting the universe's rhythm. When you fly across time zones, your body's internal clock doesn't reset instantly. It still thinks it's in the place you left. This mismatch between your internal time and local time is what we call jet lag. You feel sleepy when it's bright outside or wide awake in the dark, because your biology is still following the sun's position from thousands of kilometers away. This isn't just inconvenience, it's evidence of how tightly our bodies are tied to cosmic cycles. The sun's light, the length of the day, and even the timing of dawn are signals we've been syncing to for millions of years. When those signals change too quickly, we feel the cost. It's a reminder that we can't simply override the rhythms we inherited from the Earth's steady rotation and its journey around the sun. The strange connection between solar storms and human rest. Far above our heads, the sun occasionally erupts with massive bursts of energy called solar storms. When these streams of charged particles reach Earth, they can disrupt satellites, power grids, and interestingly, human sleep patterns. Some studies suggest that during periods of high solar activity, people report more vivid dreams, restless nights, or even shifts in mood. The cause isn't fully understood, but it may be linked to subtle changes in the Earth's magnetic field affecting our body's natural rhythms. It's fascinating. The same storms that paint auroras across polar skies might also be whispering into our dreams. Seasonal shifts in mood and the tilt of our planet. Earth's axis is tilted at about 23.5 degrees, and this tilt is why we have seasons. But it also means that the amount of daylight we receive changes throughout the year, and so does our biology. In winter, shorter days can lower serotonin levels, leading to seasonal mood shifts. In summer, longer daylight often brings higher energy and lighter moods. This isn't just cultural, it's hardwired into our neurochemistry. Our hormones respond to light exposure, adjusting sleep cycles, appetite, and even emotional balance. We are, in a very real sense, creatures of light. The tilt of our planet, a feature set in motion billions of years ago, still quietly shapes how we feel and how we live, season after season. Why people sleep more deeply in winter nights. When nights grow long and cold, our bodies naturally produce more melatonin, the hormone that helps us sleep. Even in modern cities, where we can light up the darkness, winter often brings deeper, longer rest. This may be a survival mechanism, helping conserve energy when food was scarce in our evolutionary past. The quiet, extended nights of winter also mean less sensory stimulation. Without the buzz of summer activity, our minds have more room to drift inward, settling into richer dream states. It's an echo of a time when our ancestors aligned their rest to the slow breathing of the earth itself, the silent influence of starlight on our hormones. Starlight is faint compared to the sun or moon, but it's still there, a constant, gentle presence. Before artificial light, this soft glow may have subtly influenced our body's hormone cycles, especially in places with clear, dark skies. Even today, research suggests that exposure to natural night skies, including starlight, can help regulate melatonin production and support healthier sleep. It's not the brightness that matters, but the consistency of a natural light-dark cycle. When we shield ourselves from the night sky, we also lose that silent connection to the cosmos. Letting starlight reach our eyes is a way of keeping an ancient appointment we've had with the universe for as long as humans have existed. The hum of gravitational waves passing through Earth. All around us, space-time is trembling. Not enough for us to feel, but enough for the most sensitive detectors to hear. These are gravitational waves, ripples in the fabric of the universe, created when massive objects like black holes or neutron stars collide. When they pass through Earth, they stretch and squeeze space itself, ever so slightly. It's astonishing to think that in the quiet of night, as we sleep, the planet is being rocked, gently, invisibly, by events that happened billions of light years away. These waves travel unimpeded, carrying the energy of cataclysms across the cosmos. To scientists, they're more than curiosities. They're a new way of listening to the universe, a cosmic sense of touch we only just learned to use. Cosmic rays and their invisible arrival each night. Every second, tiny high-energy particles called cosmic rays rain down on Earth from deep space. They come from exploding stars, active galaxies, and other energetic events far beyond our solar system. Most pass through us without harm, but they're a constant reminder that we live under an unending shower of cosmic messengers. Some hit our atmosphere and create cascades of secondary particles, a kind of invisible fireworks overhead. They even subtly affect technology, sometimes flipping bits in computer memory, a microscopic nudge from the universe itself. They're proof that even in the stillness of sleep, we're connected to far-off explosions and ancient energy. how solar flares disrupt our sense of time on Earth. The sun isn't just a steady source of light, it's a restless star. Occasionally it releases massive bursts of charged particles and radiation known as solar flares. These eruptions can disrupt communications, navigation systems, and, in rare cases, power grids. But they can also alter our daily rhythm. During strong solar storms, the auroras they cause can turn night into shimmering daylight near the poles, confusing both animals and people. In history, such events even made newspaper headlines as "nights that never got dark." These solar outbursts are a reminder that time on Earth is never entirely separate from the mood of our star. Planetary alignments and their subtle pull on sleep cycles. From time to time, several planets in our solar system line up in the same general region of the sky. These alignments are beautiful to look at, but they also subtly shift the gravitational balance in our neighborhood. The effect on Earth is tiny, imperceptible to our senses, but life on our planet has evolved in the presence of these quiet cosmic rhythms. While science hasn't found a direct cause and effect link to human sleep patterns, it's hard to ignore how many ancient cultures recorded these alignments and adjusted rituals, planting cycles and even rest patterns around them. Perhaps some part of us still listens, even if we don't notice it consciously. The role of eclipses in marking deep time. Eclipses, whether solar or lunar, are among the most striking cosmic events we can witness. They're also incredibly precise. The cycles that predict them, such as the Saros cycle, have been tracked for thousands of years, linking human history to the steady mechanics of celestial motion. For ancient peoples, eclipses weren't just spectacles. They were cosmic punctuation marks, moments that divided eras or confirmed the predictions of astronomers. The repeating nature of eclipses also gave humans one of their earliest tools for understanding long-term celestial cycles. To this day, every eclipse feels like the universe quietly marking a page in its calendar. Why comet returns feel like the universe keeping score. Comets are wanderers, icy bodies that spend most of their lives far from the sun, only to swing close on long, predictable orbits. Some take decades to return, others centuries. When they do, they look almost unchanged, as if they've been keeping to their own quiet appointment all this time. Halley's Comet, for instance, has visited Earth's skies since before recorded history, its returns noted by ancient astronomers in China, Babylon, and medieval Europe. Each appearance feels like the universe checking in, reminding us that its cycles are far longer than our lifetimes. Every return links generations. Your ancestors may have seen the same comet you'll see in the future. How meteor showers carry ancient time-stamped dust. When Earth passes through the dusty trail left by a comet, those particles burn up in our atmosphere, creating meteor showers. Each shooting star is a fragment of cosmic history, sometimes older than our planet itself. These showers repeat on predictable dates because the comet's path is steady, leaving behind its debris in the same places year after year. The Perseids, for example, arrive every August, like clockwork, their dust glowing briefly before vanishing into darkness. In a way, these meteors are the universe's most fleeting reminders, flashes that last a second, yet began their journey thousands or millions of years ago. The faint heartbeat of the sun's activity cycles. The sun has its own rhythm, an approximately 11-year cycle of increasing and decreasing sunspot activity. These sunspots are tied to the sun's magnetic field, which twists and flips over time. At the cycle's peak, the sun produces more flares and storms. At its quietest, its surface is almost spotless. This cycle subtly influences Earth, from the strength of auroras to slight changes in the amount of solar energy reaching us. Ancient cultures may not have understood the science, but they noticed patterns in harvests, weather, and even fish migrations linked to the sun's changing face. It's the quiet heartbeat of our star, pulsing through the centuries. Star clusters as frozen moments in cosmic history. In the night sky, some groups of stars travel together, star clusters born from the same cloud of gas and dust. These stars share an age, a birthplace, and a trajectory, making them cosmic siblings. Looking at a cluster is like seeing a family portrait from a single moment in time. Over millions of years, the stars drift apart, but for now, they remain bound by gravity. Observing them lets astronomers study how stars evolve, almost like flipping through a photo album of stellar life stages. They're frozen moments in the universe's long memory, holding their shape just long enough for us to notice. The quiet countdown of stars running out of fuel. Every star is a clock, burning through its supply of nuclear fuel. Massive stars blaze brightly but burn out quickly in just a few million years, while smaller stars like our Sun can shine for billions. This slow countdown is invisible to us day by day, yet relentless on the cosmic scale. When a star nears the end of its life, it changes colour, size, and brightness, like the hands of a clock approaching midnight. Eventually it will collapse or explode, marking the final tick of its stellar timepiece. Knowing this gives the night sky a bittersweet beauty. Some of the lights we see tonight are in their final chapters, yet still shining for us across the gulf of time. The possibility of time before the Big Bang. It's tempting to think of the Big Bang as the absolute beginning, the first tick of the cosmic clock. But some physicists suggest time may have existed before that moment. In certain models, the Big Bang is not the start, but a transition, a bounce from a previous universe that collapsed before ours began. In this view, the arrow of time could extend infinitely backward, with universes rising and falling like waves. Others propose that time itself emerged with the Big Bang, and asking what happened before is like asking what's north of the North Pole. Either way, the thought is dizzying. Our current moment could be just one chapter in a story much longer than we can see. Loop quantum cosmology and cyclic universes. In loop quantum cosmology, the universe's smallest building blocks, space and time themselves, are quantized, meaning they come in tiny, indivisible units. In this theory, the Big Bang wasn't a singular beginning, but the point where a previous contracting universe bounced into expansion. If true, this means time has no absolute start, only cycles. Universes would be born, expand, slow, and collapse, giving birth to new ones endlessly. The cosmic clock wouldn't just tick forward, it would reset again and again. The concept is both strange and comforting. Endings are never truly final, just transformations in an eternal rhythm. How entropy measures the universe's aging process. Every system in the universe tends toward disorder. This is entropy, the second law of thermodynamics. Over time, energy spreads out, structures break down, and differences even out. It's why ice melts, stars burn out, and galaxies drift into darkness. Entropy is a kind of cosmic hourglass. In the early universe, matter and energy were tightly organized. Now, they're more scattered. As entropy increases, the universe ages. One day, it may reach heat death, where energy is so evenly spread there's nothing left to power change. It's not an immediate threat. It's trillions of years away. But it's a reminder that even the grandest clocks run toward their final tick. The heat-death clock of the cosmos. In the far future, if no other forces intervene, stars will burn out, galaxies will fade, and black holes will slowly evaporate through Hawking radiation. Eventually, the universe will be a cold, dark expanse of thin particles and fading light. This is the heat-death scenario, the ultimate stillness where time, in a sense, loses meaning because nothing changes. The cosmic clock will keep ticking, but there will be nothing left to mark its passage. It's an eerie thought that the universe might one day fall completely silent, not because it ran out of space, but because it ran out of energy to keep the rhythm going. How galaxies drift apart in slow motion. Right now, the expansion of the universe is speeding up, driven by something we call dark energy. Over billions of years, this acceleration will push galaxies farther and farther apart until the night sky from any one galaxy will be almost empty. It's happening too slowly for us to see in a human lifetime, but the separation is steady, a slow motion pulling away that reshapes the cosmic map. In the very distant future, distant galaxies will slip beyond the observable horizon entirely, becoming unreachable and invisible. When that happens, the record of our shared now will shrink, leaving each galaxy an isolated island in an endless silent sea. Time as a dimension we can't fully perceive. We move through space in 3 dimensions: length, width, height, but time is the 4th, and unlike the others, we can only travel in one direction. Physics treats time as a coordinate, just like the ones that define your position in space, yet our experience of it feels completely different. Imagine space-time as a vast landscape. You can look left or right, up or down, but in time, you can only go forward. It's as if we're walking along a single path in a terrain that stretches endlessly in all directions, most of it hidden from our senses. We live inside this dimension without truly seeing it. The seconds we feel are just slices of a much bigger whole. The paradox of time travel in physics. Time travel into the future is not only possible, it's inevitable. Every second we move forward in time just by existing. But traveling into the distant future is theoretically achievable by moving near the speed of light or being close to intense gravity, where time runs slower for you than for others. The past is trickier. Most physicists believe traveling backward creates paradoxes, like meeting your younger self or changing events that already happened. Some theories get around this with closed, time-like curves, where events loop without contradictions, but no evidence for them exists yet. It's a fascinating reminder that while the equations allow for strange possibilities, reality might have its own guardrails. Why the arrow of time only points one way? We can imagine time flowing backward, glasses reassembling from shards, smoke returning to a candle. But in reality, it never happens. This one-way flow is the arrow of time, and it's tied to entropy. As disorder increases, the arrow moves forward. The laws of physics work the same whether time moves forward or backward, yet our experience doesn't. This is because the universe began in a highly ordered state after the Big Bang, and since then, disorder has been rising. Every tick forward is another step away from that initial order. It's not just physics. Our memories, our aging, even our language follow the arrow of time. We live in its current without any way to swim back. The quantum uncertainty of the present moment. In the quantum world, particles don't have fixed positions or speeds until they're measured. They exist in a haze of possibilities. This uncertainty means that defining an exact now across the whole universe is impossible. Events that seem simultaneous to you might not be to someone moving at a different speed or in a different place. This fuzzy nature of the present challenges our everyday intuition. The idea of a single universal now may be an illusion. What we call the present is just our local experience, stitched together from signals arriving at the speed of light. It's humbling to think that reality's clock doesn't have a single hand, but countless hands, each ticking in its own frame. Whether the universe experiences now at all. If time is a dimension, then the universe might contain all moments, past, present, and future, at once. In this block universe view, now is just the slice we happen to be experiencing, moving along the time axis like a needle on a record. From this perspective, the future already exists, just as the past still exists. We simply haven't reached those points in our journey. It raises a profound question: does the universe feel the passage of time, or is that sensation unique to conscious beings like us? If the cosmos doesn't have a now, then our experience of the present may be one of the most precious illusions we have. How constellations change shape over millennia. The constellations we know today, Orion, Cassiopeia, the Big Dipper, feel timeless, yet their shapes are not fixed. Stars in a constellation are not close to each other in space, they just appear that way from our viewpoint. Over thousands of years, their motions slowly distort these patterns. In the far future, Orion's belt will no longer be a straight line. The Big Dipper's handle will twist into a different curve. The sky our descendants see will be familiar, yet strange. A reminder that even the night's patterns are moving to the universe's clock. Constellations are, in truth, temporary alignments, captured only in this chapter of cosmic time. The long memory of ancient star maps. Long before satellites or telescopes, people mapped the sky with remarkable accuracy. Carvings on stone, patterns on pottery, and records on parchment preserve the positions of stars as they appeared thousands of years ago. These ancient maps are windows into the past, letting us see how the sky has shifted since. Some star positions recorded by the Babylonians, Egyptians, and Polynesians no longer match exactly. The slow movement of the stars and Earth's own wobble have altered the view. And yet the maps remain as a kind of handshake across time, proof that humans have always measured themselves against the heavens. Navigating by the slow movement of Polaris. For centuries, Polaris, the North Star, has been a steady guide in the night sky, always pointing toward true north. But even Polaris drifts. Over millennia, the position of Earth's axis changes due to precession, and Polaris will one day give up its role. Another star will take its place as the pole star. Ancient navigators who used Polaris relied on its steadiness, but the cosmic clock is still ticking. The star's reign is temporary, just a chapter in the Earth's long rotational story. The thought makes navigation by the stars feel even more magical, like walking a path that's slowly shifting under your feet. How eclipses connected ancient civilizations to cosmic time. Eclipses are so precise that they allowed ancient astronomers to predict them centuries in advance. Cultures across the world, from the Maya to the Chinese, Warriors, recorded these events, using them to refine calendars and measure long cycles like the Saros, which repeats roughly every 18 years. These moments united observation and storytelling. Myths rose around eclipses, but so did science. For many, they were proof that the heavens followed patterns, that the universe could be understood. An eclipse wasn't just a spectacle, it was a cosmic reminder that time could be measured far beyond a human lifetime. Stonehenge and other monuments as giant clocks. Scattered across the earth are ancient structures that double as calendars. Stonehenge, the pyramids, the Chaco Canyon spirals. These were not built randomly. Their stones align with solstices, equinoxes, and star risings. In their shadows and alignments, people could read the seasons. These monuments are timekeepers on a human scale, yet their reference points, the sun, the moon, the stars, are part of the universe's deeper clock. Standing among them, you feel the connection between our small, daily time and the endless sweep of cosmic time. Why time in the universe runs without pause. Unlike our daily lives, where clocks can be stopped, rewound, or reset, the universe's time flows without interruption. Stars burn, galaxies drift, particles decay, all in an unbroken sequence. There are no skipped beats, no rewinds. It's this continuity that allows astronomers to trace events billions of years into the past and predict billions into the future. Even when we sleep, when our own awareness of time blurs, the cosmic clock doesn't slow. It moves steadily, carrying us forward whether we notice or not. It's both humbling and strangely comforting, knowing we're part of something that never hesitates. How sleeping under the stars resets the human mind. Spending even one night sleeping outdoors under an open sky can shift your body's clock closer to its natural rhythm. Without artificial light, your melatonin production rises earlier, helping you fall asleep sooner and wake with the sun. Researchers have found that a week of camping can reset circadian rhythms, making people feel more alert during the day and more restful at night. The view of the stars overhead also gives a mental reset, a reminder that our small worries live inside a much larger, calmer order. It's like syncing your inner clock with the deep, ancient one above, the comfort of syncing our nights with the cosmos. There's a quiet peace in aligning your life with natural cycles, going to bed when it's dark, waking with the first light. It's the rhythm our ancestors knew instinctively and one our bodies still remember. When you match your nights to the turning of the earth and the sweep of the stars, time feels less rushed. You begin to sense its flow as something gentle, not something chasing you. In that space, sleep feels deeper, and waking feels less like an alarm and more like an invitation. Why the universe's clock might be inside us too. Our heartbeat, our breath, the cycles of our cells, all run on timing systems shaped by billions of years of evolution under cosmic rhythms. The length of a day, the pull of the moon, the warmth of the sun, they've left their imprint in our biology. In a sense, we carry the universe's clock within us. The same forces that keep planets in orbit also shape the pulses and patterns of our bodies. We're not separate from cosmic time. We're living expressions of it, drifting to sleep in the same rhythm as the stars. As you lie down at night, the earth turns you gently away from the sun and into the dark. Stars wheel overhead, each one holding its own time, some young, some ancient, some already gone but still shining in your sky. You breathe slower, your mind drifts, and without realizing it, your own rhythm falls in line with theirs. You're not just resting, you're moving in perfect time with the oldest clock in existence. How ancient timekeeping still shapes modern life. Our calendars, hours and weeks may feel modern, but their roots run deep into ancient astronomy. The 7-day week, for example, was inspired by the visible celestial bodies, the sun, moon, and 5 wandering planets known to early skywatchers. The concept of months came from the moon's cycle, and years from the Earth's orbit around the sun. Even the idea of noon comes from the moment the sun is highest in the sky, a practice used long before clocks existed. Every time we schedule a meeting or set a reminder, we're quietly echoing patterns first measured by shadows and stars. The hidden influence of tidal cycles on human history. The rise and fall of the tides, caused by the moon's gravity, have guided human activity for millennia. Fishermen, traders, and coastal communities plan their work according to the tide's predictable timing. Ancient port cities often flourished where tidal cycles allowed easy docking and departure. Even inland, tidal timing influenced trade routes and food supplies. In this way, a distant celestial body, the moon, has shaped human economies and settlement patterns as surely as any invention or law. How eclipses inspired the earliest scientific predictions. Eclipses were once seen as omens, but they also sparked some of humanity's first scientific breakthroughs. By carefully recording when and where eclipses occurred, ancient astronomers learned they could predict them years or even centuries in advance. These predictions were more than intellectual achievements. They were powerful social tools. Rulers who could foresee an eclipse gained influence, showing their alignment with cosmic order. Science and power grew together. tied to the rhythm of the skies, the astronomical roots of religious and cultural festivals. Many of today's holidays and rituals trace their timing back to celestial events: solstices, equinoxes, harvest moons. These astronomical markers determined when communities celebrated, planted, or prepared for winter. Even in modern cities, festivals often happen close to these seasonal turning points. We may no longer track them with stone circles or shadow lines, but the timing remains embedded in our cultural DNA. How reconnecting with cosmic time changes perspective. When you start noticing the moon's phases, the tilt of the sun's path, or the slow drift of constellations, time feels different. It stretches. It deepens. Days are no longer just items on a calendar. They're part of a much older pattern that has been in motion since before humanity began. This shift doesn't require abandoning modern life. Even a few moments under the stars, or watching a sunrise without distraction, can pull you back into sync with the universe's unbroken rhythm. And in that rhythm, there's a kind of quiet reassurance that no matter how fast life feels, you're always exactly where you should be in the great turning of time. The whisper of ancient calendars in our language. Even in the way we speak, traces of cosmic time remain. Words like month come from the moon's cycle, season from the turning of the year. The names of weekdays in many languages still honour celestial bodies: the sun, the moon, and planets visible to the naked eye. We may not think about these origins, but they are quiet reminders that human timekeeping began with the sky. Our vocabulary carries the imprint of the universe, echoing a time when the heavens were not just observed, but woven into daily life itself. The link between agriculture and celestial timing. For most of history, farming was humanity's heartbeat, and it was set to the rhythm of the sun, moon, and stars. Planting and harvest dates were chosen by observing the length of days, the position of certain constellations, and the phases of the moon. A single misjudgment in timing could mean hunger in the months ahead. In this way, cosmic time wasn't abstract, it was survival. Even now, many farmers still follow lunar planting calendars, blending tradition with modern science. How navigation by the stars shaped exploration. Before compasses, before GPS, explorers steered their way across oceans by reading the night sky. The height of Polaris above the horizon told sailors their latitude. The rising and setting of specific stars marked seasonal winds and safe passages. Entire trade routes were mapped by celestial navigation, connecting distant cultures. The stars weren't just guides, they were the lines on the first global maps. And every journey was a kind of partnership between human ambition and the universe's steady clockwork. The role of the equinox in balancing the year. Twice a year, day and night are almost exactly equal in length, the equinoxes. Ancient builders aligned temples, pyramids, and stone circles to mark these moments. They signaled the start of planting or harvest seasons and were celebrated as times of balance. The equinox is a reminder that the year has its own heartbeat, a rhythm of light and dark that repeats with perfect regularity. Even in the rush of modern life, this balance still arrives, right on schedule, as it has for billions of years. The enduring pull of cosmic time on human imagination. From the first cave paintings to the latest space telescopes, we've looked upward and seen not just light, but meaning. The universe's clock has inspired myths, guided journeys, shaped calendars, and now drives our most advanced science. We may measure time in seconds, but our imaginations measure it in star lifespans and galaxy rotations. Cosmic time reminds us that we are small, but also that we are part of something vast and ongoing, a story that began before us and will continue long after. How lunar eclipses reveal Earth's shadow in space. During a lunar eclipse, the Earth slips directly between the Sun and the Moon, casting its shadow across the Moon's face. This shadow isn't just darkness, it's curved, a direct visible proof that our planet is round. Ancient astronomers used this observation to argue for Earth's shape long before satellites confirmed it. The coppery glow the moon takes on during totality comes from sunlight bending through our atmosphere, filtered by all the sunsets happening on Earth at that moment. In that brief time, the moon becomes a mirror of our own world's presence in space. How planetary transits sharpen our cosmic calendar. When a planet passes directly between the Earth and the Sun, we see a tiny dot crossing the Sun's surface. This is a planetary transit. These events are rare and predictable, often centuries apart for certain planets. Astronomers have used them to measure distances in the solar system with incredible precision. Transits are like precise ticks on the universe's calendar, moments where celestial geometry lines up so perfectly that we can use them to anchor our understanding of cosmic time and scale. The subtle drift of the constellations through precession. Because of Earth's slow axial wobble, the constellations slowly shift position over thousands of years. In ancient Egyptian times, the constellation Leo rose with the sun during the summer solstice. Today, it does not. This gradual drift changes which constellations mark the seasons, subtly altering the backdrop of human history. If you could live long enough, you'd watch the familiar seasonal skies slowly slide into new arrangements, the clockwork of the heavens changing its face. How ancient star risings mark the start of the year. Many ancient cultures began their calendars not on January 1st, but on the first appearance of certain stars before dawn. For the Egyptians, the rising of Sirius heralded the annual flooding of the Nile, a crucial event for farming. For Polynesian navigators, the seasonal rising of stars marked safe times for long voyages. These heliacal risings were cosmic milestones, linking the rhythms of the heavens directly to survival and celebration on Earth. The rhythm of meteor showers as annual sky anniversaries. Each year, meteor showers return on almost the exact same nights as Earth crosses paths with the dust trails of ancient comets. For sky watchers, they become annual anniversaries, the Perseids in August, the Geminids in December. Their reliability is comforting. No matter what has changed in the world below, the streaks of light will appear on schedule, just as they have for centuries. They're one of the simplest ways to feel the heartbeat of cosmic time from your own backyard.